Okay, so let me start with the lemma that justified the very first step of the previous proof, and the idea is to take a discrete random variable, and so you can try to generalize this on your own, but here I've taken y to be in the natural numbers and possibly infinite. And so that means y can take on the value 0, 1, 2, 3, and all the way out to infinity. And so let that be random, meaning it has some distribution. And potentially there's some positive probability of y being infinite. And we'll kind of discuss that case at the very end. So, how do we prove this, right? This is the identity that I used in the very first part of the proof there. It says that the expected value is the sum over these what are essentially tail probabilities, right? The probability that y exceeds the number k, and you're summing over all k, and a key here is that k must start with 1, and you can adjust this proof for other values, but not necessarily things in n. You can even adapt this for continuous random variables, but here let's just stick to this more simpler setting. The main idea that you're welcome to kind of carry over and try to adapt this proof to other settings is this identity here. So why is this true, right? What am I doing? I'm summing now from k1 to infinity indicators that are 1 when k is less than or equal to y, and 0 when k is greater than y. So the question is, how many of these are going to take on the value 1, right? How many of these indicators are equal to 1 in this giant infinite sum? Well, the claim is precisely y of them, and this is where counting from 1 is important, right? So if is 1 less than 1, so if 1 is less than or equal to y, I'm going to add that to the count. If 2 is less than or equal to 1, I'm going to add that to the count. If 3 or 4, and so on. And so when, how many of these have I counted, right? I'm going to count from 1, 2, 3, all the way up to y, right? And I add 1 each time, therefore I get y in the end, right? So this is a very clever trick, and you can try to convince yourself that this is true, and you can even get an alternative expression, right? When you, for example, sum from 0, then you may want to put a k strictly less than y, which changes this identity a little bit. So let's keep going, right? But once you have this identity star here, we're in pretty good shape, right? Because then I take the expected value of both sides, I arrive at here. Then there's a little bit of a catch here in moving this expectation and an infinite sum. You have to do that very carefully, but I'll tell you a quick sort of rule for when you can do that. When the random variable inside is non-negative, or just in general bounded below, right? Never, for example, is never below some number, you can do this. But in particular, when you see something non-negative inside the sum, you can exchange it with the expectation, which is what I've done here. In general, you do want to be careful when exchanging limits and expectations, and we've already seen examples of this. So then, this one, the last step, is trivial, right? The expected value of the indicator is just the probability of that event. And that concludes the proof, right? And so this didn't have anything to do with the number of visits to that state little y in particular, right? This is true for any discrete random variable. And then the last note on infinity. So how do we verify this? Notice that I've never actually mentioned the word infinity here. Let's make sure that it actually works for the case when y is infinite with positive probability. When that's true, you immediately know that the expected value is infinite, because you would take infinity times a positive probability, which will give you infinity on this side. And now the question is, will this then be infinity? Well, clearly so, because when y, if y is allowed to take on the value infinity, then it's greater than any finite number, right? Any natural number k with a positive probability. So when you sum up a bunch of positive numbers that are, the same, right? There's just going to be this, so summing the same positive value over and over and over infinite amount of times, you'll get infinity on this side as well, verifying this identity for the case when y can take on the value infinity. Right there, it's a trivial equality. Infinity equals infinity. Okay, so that takes care of that lemma. Let me mention this strong Markov property, and this is a very general result that I want to try to impart to you. And hopefully this will be useful. The idea is first to define this expected value calculation. So you pick your favorite function that's bounded, right? So we're going to pick a bounded function h. So you can think of your favorite bounded function. Maybe it's a sine or a cosine, or some kind of function that maybe grows even exponentially, but then gets cut off at somewhere. So the idea is that it does have to be bounded. And there are ways to kind of get more generality here, but there's no time to really get into those details. But the idea is to define this function gk of x, where x is the starting state, right? So I think this expectation you have a good handle on, and once h is picked and once k and x are decided on, you can potentially compute this, either analytically or on a computer or whatever, wherever else. This is a well-defined expectation, right? It's a function of x, right? Anytime you change the starting point x, this calculation is likely to change. So what's the statement of the strong Markov property? Well, it says that for any finite hitting time, and there's a more general version with what are called stopping times, but we're dealing with hitting times for now, and this is going to be fine. So a hitting time is essentially the first time when a Markov chain x hits something, right? We've already seen an example in the screenshot again, right? This is tx is the first hitting time of the state x. You can generalize this. You can we'll discuss this later. You can write a hitting time of, for example, the set A, right? A set of subset of states. So you're maybe there looking for the first time that the chain enters some specific set. So that's also a hitting time. So we'll come back to that in our examples. But here's the punchline, right? So the punchline is that if you have this expectation where you're looking at the expected value of h at some time that's random plus some k, right? So you're basically looking at k units of time after the chain x hit some state or set of states, conditional on the entire history up to that random time. Well, that can be evaluated with this right hand side here. So here you want to be very careful. When I write this, I do not mean that we're going to take this xt, which is potentially random also, right? It's possible that this is random, sometimes it's not, but this potentially is a random variable. I do not mean for you to take this and put it and somehow try to involve this into this computation. The idea is to compute this function for any value of x first, and then to evaluate this function at the random variable xt. So how is this helpful for our previous proof, right? The idea is to condition on these trips that we took, right? We decomposed the number of k visits to y as a trip from x to y, and then a round trip from y to y, and so on and so forth. And those were random times, right? Each return time, each visit time to state y was random, right? It was tyk, right? Those were random times. And so this strong Markov property lets you condition on a path up to a random time, right? This is a path, for example, from m equals 0 to t. And you can do this kind of over and over and over and condition like so to basically prove that independence property that we discussed. So if you like, that's an extra kind of challenge exercise to go back to that previous proof and then show that step where I use the independence of all of these trips, and that independence can be argued with this strong Markov property. A couple of more notes here. If you let hy be the indicator function, which is certainly bounded, you will get something that looks a lot more like the Markov property, because this expectation becomes a probability that x is equal to y, to some state y. So you can actually convert this into a statement not in terms of expectations but in terms of probabilities. And then what's another note? The other note is, in the case of tx, which is the first hitting time of x, you can very easily tell that this is not random at all. This is in fact equal to little x, right? That's little x, not big X. Shorten it a bit. So, right, the idea is pretty clear. What is the value of the Markov chain x at the very first time that it hits state little x? Well, it's little x. So hopefully that's clear and helpful, and if you kind of want to challenge yourself, try to see if you can apply this strong Markov property in the previous proof. And so I ran out of board space, and so in the next clip I'm going to have to kind of pick up on this previous theorem and show you how it's useful for determining when a state is recurrent.